Good morning, everybody, and happy Wednesday. Tis Wednesday, not Tuesday. I did record this yesterday, but for some reason the file disappeared into the ether somewhere. So, for the second time, big shout out to Leo. And let's start talking about forces and force vectors in relation to Newton's laws of motion. So let's just remind ourselves of a couple of things. First off, we are familiar with the concept of vectors as being scaled arrows, so that if, for example, I wanted to represent a journey that I did using vector arrows, I might say I went 10 meters in one direction, and then perhaps I did a second journey at right angles to that first one of, looks a bit smaller, let's call that 8 meters. Ooh, that doesn't look like an 8. 8 meters, it still doesn't look like an 8. 8 meters. Then I could combine those two journeys and say, well, what could I do? What single journey could I do to get the same effect? Right? And obviously that would be this blue arrow here, and I could find the length of that blue arrow easily enough. I'm going to call it R. R is generally one of the letters that we use to represent a resultant vector, or in other words, what you get when you combine two vectors. So in essence, what we're saying here is that R, the blue arrow, is what we could do instead of the two red arrows. And the point is, we end up in exactly the same place. So in a very real sense, it doesn't matter whether we actually followed the two red arrows or the single blue arrow, whose length or magnitude will obviously be equal to that sum, which is equal to, let me just work it out, 12.8 meters. However, although walking 12.8 meters would tell you how far to go to replicate those two red arrows, it would not tell us in what direction we need to go, right? You could walk 12.8 meters in any direction. Doesn't mean you'll end up in the same place. So we need a directional component. That means finding this angle here. That angle is easy enough to find if we remember our trig rules. We've got the opposite, we've got the adjacent. So tan of theta will be equal to opposite, which is 8, over adjacent, which is 10. Quick side note, that's how I draw a letter theta. You're probably more used to seeing it as a circle with a line through it. Same thing, doesn't matter. So, tan theta is 8/10, therefore theta must be equal to the inverse tangent of 8/10. And if we do that on our calculator, 8 over 10 inverse tan is 38.7, rounded, 38.7 degrees. So we can replace the two red arrows with a journey of 12.8 meters at 38.7 degrees below the horizontal, or below the positive x-axis, or we could also put it in compass point terms. That would be, let's see, west and south, so south of west. How do we then apply this to what we know about forces? Well, we can do the same thing with forces. It's not quite so easy to conceptualize because you can't actually see a force, and obviously you can't really draw a force on a page because it's not something that you can see. Nor is it as obvious that you can use scaled arrows to represent forces, but you can. So let's look at a quick example here. If I have a box that is experiencing two forces simultaneously, then just your knowledge of the world and how the world works tells you that that box is going to move in a bit of a diagonal, right? It's going to go off in this direction. And you're right, it would. But what we need to be able to do is to say, in order to do calculations and modeling of real-world situations using our equations and using our knowledge of forces, we need to be able to put numbers on these things. So like if I wanted to replace the 2 black arrows with one single blue arrow, what direction should it be pointing in and how long should it be? And it just turns out that if we do this, we will get an answer that works in the real world. So we're just doing geometry on the length of lines, but it translates back to the real world successfully. And the universe doesn't give a monkey's tail whether we have this situation with just the single blue arrow, or instead we have the 2 black arrows acting simultaneously. They both give the exact same result, so the universe doesn't care which one is true. And that helps us out because there are lots of situations in which it's more useful for us to have the 2 black arrows than the single blue one, in which case we can do that through geometry. We can replace the blue one with the 2 black ones. Or there are also cases where we're the other way around. It would be more useful to figure out what single vector can replace those 2 vectors. And we're going to practice doing both of those things. But let's start with something much more simple. We'll start with a single box and a single force acting on this box. So here we go. Here is a box with a force, let's call it F, acting on it. And what we know about Newton and his laws tells us that this box will accelerate to the right. Now, when we spoke about it yesterday, we used the term move. The box will move, and it will move faster. But in reality, what we're dealing with here is acceleration. So the box will accelerate to the right. And it will become clear why we talk about acceleration as opposed to movement a little bit later. So that box accelerates to the right. Why? Because the force is to the right. That's obvious. What happens, though, if we have a box with more than one force acting on it? And remember, these force arrows are designed to be scaled, as in the length of the arrow tells you the size of the force. So here, let's call that one F, and let's call that one F2. So let's call this one F1 and the other one F2. Now clearly, F1, the arrow, is longer than F2. That tells us that the size of the force F1 is bigger than the size F2. And if this was a tug of war, it's obvious that F1 is going to win, and that box is going to do what? Well, it will accelerate to the right. So again, the box will accelerate to the right. Now, why? Well, you can't say it's because the force is to the right. There's more than one force. We've got to be more specific than that. So up here, we were able to say that. The reason why is because the force is to the right. But we can't just say that. Here there's more than one force, so what do we do instead? Well, we've got to say that the overall force is to the right, and the physics term for that is net. So the net force is to the right. We can express that mathematically. We use this symbol here, capital sigma. So sigma F means net force. Now, this sigma is used to mean sum of, right? You're used to that from math, the sum of. So sigma F, sum of the forces. And you might think initially, well, hang on, sum of the forces would mean F1 plus F2. That would just be adding the length of those 2 arrows. That's going to give me, well, it's not going to give me something that I'm going to be able to use. Your instincts tell you that in a tug-of-war situation, what you really need is F1 minus F2 to give you the size of the overall force to the right. And your instincts are correct. So how do we square this circle? How do we make use of the sum of term and make sense of this? Well, The reason it works is because direction is important. Remember, vectors have both size and direction. And here is the normal